Okay, yeah, go for it.
And you can see my screen, right? Okay. Let me start. Before we start, I would like to give you a big thank you to everyone for today's attendance, and do thanks for my all supervisors, they help me a lot. And the topic for today is hyperparameter optimization for graph neural networks, molecular property prediction. I think it looks quite a broad topic, because the content for today's talk is from my 4 papers, so it's a little bit more. So, but I will try my best to go through every details. Most of you interested. And, okay. And today's presentation is divided into the 4 parts. The first part is the graph neural networks. I think most of you are interested. And the second part is hyperparameter optimization. And the third part, I would like to show some experiments result, but just a part of experimental data from my papers. And finally, I will give a conclusion and future work to end today's presentation. And after that, you can ask me any questions, and all comments or suggestions are welcome. And in the graph networks part, I would like to use 3 questions to cover this part. By answering these 3 questions, you will know what is graph networks, and you will know the development, the situation right now for the research of graph networks, and also we will introduce what did we do by using GNNs for molecular property prediction. And by the way, the reason why I choose the problem of molecular property prediction is because my PhD is related to the EPRC project manufacturing methodology, which aims to develop a self-healing material. So I would like to find a model which can suggest the practitioners in molecular domain or in material domain. So the model probably can be well trained. After well trained, the practitioner can use the model to predict something, and they can get some information to facilitate their research, rather than to do a lot of tests or experiments in the lab. So in this way, it can reduce the cost of the experiments in lab. And okay, and let's start the first part. Before we know the graph neural networks, definitely we need to know what is graph. I think a graph at here is not images. In graph theory, a graph is a data type, right? A graph is made up of nodes and edges. And in our real life, there are a lot of graph data, like our social networks, roadmap networks, and also molecular graphs. And in molecular graph, the atoms correspond to nodes, and the bond correspond to the edges. And let's imagine when we apply the traditional machine learning methods to solve the graph-related problems, it's really hard. It's definitely impossible, probably, to directly operate SVM support vector machine on graphs, right? Because the first step we need to take is to generate handcrafted features. But that's compared with the traditional method. GN has the ability to learn the features, to learn the representation for graphs during the layers, right? Here. And how GN learns the features. So the GN broadly follow a recursive neighbor aggregation scheme, which each node aggregate feature vector of its neighbors to compute its new features, new vectors. Let me give a quick example, probably because the conception is very more abstract. If we have a node at here, it has two neighbor node. And if we want to learn the representation for this node, right, R representations, we aggregate, we aggregate the information from here and here to link to generate representations for this node. And most of GNN follow this idea. And another feature for GNN is layer-wise. After k iteration of aggregation, a node is represented by its transformed feature vectors, which capture the structure information within the node's k-hop and neighborhood. Because in the layer 1, you get the information from these two nodes, right? If you want to learn the representation for this node. And if both these two nodes have their neighbors, so in layer 2, these two nodes will be updated already by their nodes. And so in the layer 2, this node will capture the information, the whole node at here. And I think it's very abstract at this stage, but don't worry about this because I will give an example and we will discuss this in details later. And here, I think GNN is a very hot topic in deep learning, and there are quite a lot of different researches from this area. And according to the types of aggregation we define here, right? Aggregation. The GNNs can be classified into the two types, the spatial one and the spectrum one. And in the spatial one, it has two types. The first one is called message parsing, and the second one is called convolution, which is inspired by this one, the convolution, which is inspired by the convolution in computer vision. And most of molecular GNNs are rooted from this one. And the neural fingerprint model we also call the GC, which is the one we used in all our experiments. And we definitely will explore and to discover more different GNNs in the future. And the reason why we call it the GNN is a spatial GNN because the aggregation in the spatial GNNs is a spatial manner. It's like, for example, which is similar to the convolution in computer vision. If you have a filter, you will sweep the filter over the images, right? It's a spatial manner rather than the spectrum. And compared with the spectrum GNNs, it is very, very mathematical. It originated from signal processing with the Fourier transform and Laplacian matrix and eigen decomposition. And in the next page, I will give 3 examples for the messaging parsing, convolution, and spectral GNNs. And in deep learning fashion, people use to combine some techniques together to create new things. So same as the GNNs, people combine the GNN with the attention mechanism and also encoder, and also people proposed graph GAN. And according to the types of tasks, we can classify the GNNs into the supervised, semi-supervised, and unsupervised learning. And we focused on the supervised learning. As we discussed before, my PhD is in the background of the EPRC project. And my purpose of using GNNs is I collected the data from the lab, and I want to use the data to train the model. And after I trained the model, I hope this model can help the practitioner in the material science to get the useful information before they conducted the physical experiments. Okay, and in this page, you can see two GNs, right? The first one is called the message passing, and the second one is called the convolution. The convolution is a neural fingerprint, is also called the GC, is the one we used. They are quite similar if you have a look, right? But my answer is actually yes, because the author Justin proposed a framework called the messaging passing framework, and he pointed out most of genes can be concluded in the framework. But okay, and I think the genes I showed at here is used to learn the atoms representations, right? Like here, M represents the node V, or V at here means atom V or node V. In order to learn the features, the representations for the node V, what we need to input the itself and the neighbors representations and their ages into the messaging function. M denotes the message passing function with something and here to generate the message and here at the k-means layer. Okay, we need to take the information, the representations from the previous layer as the input for the next layers. And after you get the information M, so you want to compute the new representations for the node V, right? You want to compute the new one. So we need to use the update function. And here, we input the aim and here and with its representations, the node V's representations together to generate the new representations H. And it is noted that aim function and U function are generally implemented by the neural networks, and people, they are trying to propose the different neural networks, the different structure, the different activation functions or something like that to approximate the messaging function and update function. In contrast, the convolution and here, the GN convolution and here is proposed by the David. Okay, it's also called the neural fingerprint because after you use this GN, you can generate a fingerprint. A fingerprint is a representation used in chemical area, and it's like ID, but it's numerical for each molecules. So by compute the distance between the different molecules of the smile of the fingerprints, the distance will measure the similarity of different molecules. And the convolution GN and here, the first step, you need to take the summation, right? The summation of itself representations with neighborhoods representations to generate V. And after you get the V, you use V times W. And W at here is learnable parameters. And I need to point that the W is quite interesting at here, because W you can see is N, superscript by N, and with K means the layers, right? And in each layer, you have a set of W, like W1, W2, W3. And the purpose of those W's, because if your atom has one neighborhood, you use this weight. If your neighbor, if your atom has 2 atoms, neighbor atoms, use this weight. And your atom, if has 3 atoms, you use the, or if your atom has 3 neighborhood atoms, you use this weight, right? And David also pointed out that an atom in polymer have maximum up to the 6 neighborhood atoms. So W should be stopped at by the 6. Okay. The next GN is called the spectrum GN. It's obviously it's totally different to the previous one, right? Because previous one, whatever the message passing or convolution, they proposed for learning the repetitions for per node, right? Because this H is for the atom or an node, for a node. But here is capital H. And the capital H is a representation for a graph. And also, like I mentioned before, spectrum GN originated from signal processing is more mathematical. And the D at here is degree matrix, A is adjacent matrix, and the D with tilde and powered by negative 0.5 means normalization, and W is also learnable parameters. But from my perspective, I do love this GN because it's strictly follow the layer-wise rule. Because you can, if we set this part as A, you can write down this equation, follow the layer-wise rule. If you take more layers, so you can write down the A, and here HK, WK, with the activation function, and WK plus 1 A in the next layer for the, and you can add more layer just by add more parameters. So it's very layer-wise. And to better understand what is degree matrix and adjacent matrix, let's see this picture. And on the left side, we have a look. We had a graph, right? And the degree matrix is a diagonal matrix. The elements on the diagonal line are the degrees for each node. Let's see if we have a look at about the node 1. Node 1 has 2 neighbors, right? 5 and 2. So the degree here is 2. And the adjacent matrix also, let's have a look about the node 1. So node 1 is connected with node 5 and node 2. So the 0 is changed from 0 to 1 if they are connected, right? 1, 2, 3, 4, 5, 6. So node 2 and node 5, they are connected. 0 is changed from 0 to 1. And Laplacian matrix is equal to degree matrix minus adjacent matrix. The connection between the Laplacian matrix with the spectrum GN is supported by a lot of equations and series, but we just skip this part and maybe leave this part. If you are interested, we can discuss this later. Okay. Okay, let's introduce our work. And definitely, after you get the repetitions for the nodes in a graph, you can do a lot of work, right? Because you have already got the input. You can do the graph classification. You also can do the graph regression. And for the node level tasks, you can make the prediction for the nodes. You can classify nodes. You can predict individual property for node. You also can do the node classification, clustering. And in the last one, you can do age level prediction. Like if you have a social network graph, you can predict adding two people, their relations, like families or partners, colleagues, or something like that. And what did we do by using graph networks? It's absolutely molecular property prediction, right? And because we want to predict a molecular property, we need to input the moleculars. And the input for us, for our experiments, are smiles. Smiles? This is smiles. Is a string to store to see if moleculars. So they are equivalent. You can use some Python library or other tools to generate smiles for any moleculars. You also can use those tools to convert smiles back to the graphs, because we need to input the graph to the graph neural networks. So we give the smiles at first to our program and transform the smiles into the graph at first. And then we input the graph into our graph networks. And at the first layer, as the input layer for the graph networks, the atom features include the element, degree, attached hydrogen atoms, and implicit valence, and etc. And after we get the molecular graph and how we process them, let's see the framework we proposed in our workshop paper. This is molecular, right? On the right side, this is molecular graph. We input this graph into the graph layer because we divide our whole framework into the two parts. The first part is called graph layers part, and the second part is called task-specific layers. In the first part, graph layers, the main work is aggregation, is to learn the representations for each node, right? And how we learn the representations for each atom, each node. Let's see an example. If we want to learn right? If we want to learn the representation for this node, for this carbon, in the first layer, we take the information, take the features from the oxygen, nitrogen, and the carbon at here, following the red arrows to compute the new representations for the node, at here, right? And the ellipses at the bottom means this kind of operation will swap each atom iteratively to compute the representation for each node, for each atom. And you might notice that the ellipses at the right side, which means how many layers you want to use. Because like we discussed before, if you have the 2 layers, it means you will capture the information from the two host neighborhoods, right? Let's see. So this is at the layer 1, right? After you get after the layer 1, this node receives the information from the oxygen, nitrogen, and the carbon. And in the layer 2, this atom also receives the information from the nitrogen, oxygen, and carbon. But right now in the layer 2, the nitrogen and oxygen and this carbon have already updated by their nodes, right? Because the nitrogen and, for example, like nitrogen and here, if we want to update the nitrogen, the carbon and here, and the atom and here, also this will update the nitrogen. So it means in the layer two, this atom is updated by their neighbor's neighbor, right? So it means K-hoops, right? And after you take the several graph layers, you will generate a matrix at the right side. The matrix, the row vector, every row vector is for an atom, is nodes representations. And if you want to, after you get the representations, you definitely want to use those representations to do different various real-world problems, downstream tasks. And generally, we need to take another step. It's called readout. The reason why I draw the readout cross over the two parts because the readout operation sometimes is already defined in the graph layer, and sometimes not. It depends on specific graph networks. For example, like our the neural networks, the graph networks we used called GC, neural fingerprint, it implicit define the readout-like operation already in the graph layer. So for the GC, we won't see the matrix actually. We will get a fingerprint, a vector, after graph layers. And after graph layers, you will get the vector and here, right? So reshape is kind of reshape. And you can input the vector to the fully connected feed-forward neural networks to whatever any tasks you want to do, the classification or regression. And here, but you might note there are quite a lot of hyperparameters in this framework, right? In this framework, like how many graph layers, and how many learnable parameters you used in the graph layers, and how many flicked layers here, and what's the activation function for the flicked layers, and also the size of flicked layers. So we turn to study hyperparameters. So Stephen pointed out deep learning algorithms are very sensitive to many hyperparameters, and from our perspective, graph networks might face more challenging HPO problems as input is irregular data structure, and the framework looks more stochastic than the traditional neural networks. Okay, and let's get in the next part is called Hyperparameter Optimization, HPO. And also we will use 3 questions to cover this part. The first question is about what is hyperparameter optimization. And in the second question, we will introduce some hyperparameter optimization approaches. And the last question is which types of GNNs hyperparameters to optimize. We conducted the experiments to verify to find the answer about these questions. And the types of graph networks we classify into the graph layers and the task-specific layer hyperparameters. So there are 2 types. Okay, let's see the problem statement of what is HPO. if we have the learning algorithms A, if we have the learning algorithm A, and it has many hyperparameters, and all these hyperparameters forms a search space, form the entire search space, right? And our goal is to find one lambda from this space, and the lambda will be loaded, configured into the learning algorithms, and train on the training data set and evaluated by the validation data set. And we will get to the loss as well, right? And V at here is a measurement of the loss. And our goal is to find the lambda at risk, right? We want to find the lambda at risk with the minimum loss. Before we to know the HPO approaches, let's just see some quick introduction about the HPO. HPO can improve the performance of machine learning algorithms, and HPO can improve the reproducibility and fairness of scientific studies. But from our perspective, a direct impediment is to select appropriate hyperparameters to achieve satisfactory performance with lower computational cost, right? It's back to the problem statement, because every time, the reason why we said it is a costly problem, because every time if you want to verify the lambda, you want to evaluate lambda, you have to train the A with lambda from scratch. It costs us much. And in order to elevate this kind of issue, there are quite a lot of state-of-the-art methods. According to the taxonomy by Hunter, the HPO approaches can be classified into the black box optimization and multi-fidelity optimization. CMA-ES and TPE are two the state-of-the-art approaches in HPO problems. And both of them belong to the black box because they treat the model, the GNN, in our problem as a black box model. You only feed the hyperparameters into the GNN, and you will get you only get the feedback, the loss. You won't have any access to the gradient information. And from another angle, people proposed multi-fidelity optimizations. Compared with the black box optimization, multi-fidelity optimization approaches focused on how to efficiently allocate limited computational resource to the promising solutions, right? Because, like, let's, for example, if we have the 1, 2, 3, 4, 5 hyperparameter settings, and originally, if we have a GC also, and the GC with preset 100 epochs to run. And if we run if we want to evaluate everyone, we need to like run almost 500 epochs, right? And it takes time. And by using multi-fidelity optimization, people will discard a portion of them, like and only keep the promising candidates, the solutions, to continue, like early stopping. So probably in the 50 epochs, the 50s, the 1 and the 2 and 3 will be given up, and that's the multi-fidelity. And let's see the HPO approaches we focused. And the first one is random search, because it is considered a baseline for all HPO problems. And the same CMA-ES and TPE, we also conducted a systematic comparison of random search and CMA-ES and TPE, and, which is published in the GEICO conference this year. And besides, we also proposed our own HPO method, which is called HISCA. It's a genetic algorithm with hierarchical evaluation strategy. And in order to improve the HISCA, we also proposed TSM. It's called tree structured mutation, and which is published in the CEC conference this year. And random search, I think everyone is very familiar with the random search, right? It's just an approach. It's very simple. It's an approach that uses uniform probability in determining iterative procedures at the price of optimality. And even it is very naive and simple, but it is indeed helpful for handling many yield structured and global optimization problems. And Bergstra holds the opinion that random search is a natural baseline for HPO methods. And in our GEICO paper, we conclude that the random search TPE and CMA-ES approaches into the framework of HPO problems. So the T at here means the trials, the total number of the trials. It means how many times you will do in the how many times of evaluation you will do, and every time you sample new, you use a uniform distribution to sample a new candidate lambda, and evaluate lambda t, and you record the optimization information by h. And after all, you get the h, and by sorting the h, you will find the best solutions, right? And the next one is CMA-ES. I think this is very profound method. There are quite a lot of theories and equations behind of this. But due to the time, we can't go through these very details. Just to briefly to describe this method, CMA-ES is called covariance matrix adaptation evolutionary strategies. So it's from evolutionary computation. The G at here means generation, and K represents the size of population. It is supported by the multivariant distribution. So every time you call the multivariant distribution, the right side, the part on the right side, to sample new solutions. So X equal to the lambda hyperparameters. And there are three components in the this equation. So the mean, and sigma, and covariance C. And definitely during the evolution, during each generation, you have to update these parameters. And after because you want to find the shortest path to the optimal solutions, right? So people propose to use the recombination and movement to update the aim. And they also use the evolution path to update the sigma. And by combining rank 1 and rank mu to update the covariance. And the novelty of CMA-ES is because of combining the rank 1 and rank mu. In this way, the CMA-ES is benefited by the information from the entire population and the information about the correlation between each generations. And I think because of rank 1 and rank mu, it's a kind of a balance between the exploration and the exploitation. And we also conclude the CMA-ES into the framework of HPO. And it is noticed that the different one compared with the random searches, because we needed to use the information, use the historical information to update the uniform multivariant unit normal distribution. And another state-of-the-art approaches for HPO problem is called TPE, tree structured Parson estimators. It's based on the Bayesian optimization, but traditionally people employ Gaussian process as a surrogate model in Bayesian optimization, but TPE use a density function to directly model two set of hyperparameters here, two set. The first set is called good hyperparameters, and the second set is called bad hyperparameters. And how we to judge the good or bad, we can see the loss, y. If the y less than the y at risk, it is good, and otherwise it is bad. Because we model the hyperparameters directly, so we can use this function because the hyperparameters in this function modeled is what we want, right? Because they are good, because their loss are less than the threshold. And we can use the function L to draw many samplings. And after we draw the samplings, we want to choose the most promising one. We can use the expected improvement to decide which one is selected as which one is returned to the user to take a further evaluation on the objective functions. And the EI expected improvement is equal to the L lambda divided G lambda. Okay.
James, just to say that you've got about 5 minutes left, or 5 to 8 minutes left before.
Okay, thank you so much. Okay, thank you. Okay, this is also the framework we concluded the TPE inside of our HPO framework. And okay, let's quickly show our how our approaches is called HISCA is genetic algorithm. We employed the classical evolutionary operators, crossover and mutation, and the single point mutation and single point crossover. We choose a p point, randomly choose a p point, and I swaps the portion on the right side to complete crossover, and by changing the value on the p position from the 1 to 0 or 0 to 1 to complete mutation. And our contribution for the genetic algorithm, we proposed the fast evaluation. It's kind of multi-fidelity optimizations because we don't use the. Okay, let's just directly see the process of our HISCA algorithms. So originally the population generated, right, and they are sent to the full evaluation. So if the preset epochs is 100, every individual will be every hyperparameters will loaded with the GC to run the 100 epochs and to take evaluations. But from the second generations, we use the fast evaluations. So it means we use this equation The 1 is first epoch, and the T is a preset epoch. Let's see, like the epoch. And we find we only keep the 1 with the largest difference, because we think they are promising. And after that, we, in order to improve the HISCA, we proposed the tree structure, the mutation. We use the tree to record the information during the evolution, and also use the information, the information recorded in the tree to guide the further mutations. And this is the diagram process of our TSM with our HISCA with TSM. Okay, and the final part is our experiments we've done in our papers. And there are 4 groups experiments: the HISCA with versus with Bayesian optimization, and the HISCA loaded with TSM, and a comparison study for CMA-ES, TPE, and our root mean square errors, and also which hyperparameters to optimize. And all our experiments have been conducted on the 3 datasets: ES, OL, and FreeSolve, and lipophilicity. And by the way, lipophilicity they are very important molecular dataset, because, for example, like lipophilicity is very, very important for the drug discovery, because lipophilicity will decide the metabolism and the intake of drug. And all the experiments I will show, like the mean root mean square error is obtained by the mean of the 30 times. So this is the first. Okay, this is the first our experiments we've done to compare HISCA versus with Bayesian optimizations. And in the first data set, our HISCA achieved a better performance. And in order to verify the improvement, we conducted the t-test. It shows a significant difference. Sorry. And the hyperparameters we optimized at here, LR is learning rate, SB is bench size, and SF and SG is, SF is here, the size of flicking layer. The number is defaulted 1. And the SG means the size of graph convolution, the hyperparameters used in here, and the default is the number of the graph layers is 2. And also in the second data set, our HISCA outperforms the BHO. And the last one, in the last data set, lipophilicity, even BHO has less root mean square, but according to our t-test result, it doesn't have any significant difference. Also, we conducted the experiments about HISCA with TSM. And in the first data set, there's no significant difference, and it means probably no improvement. And it's a little bit disappointed in the second data set. HISCA without TSM outperforms the HISCA with TSM. And because the potential reason at here is because the FreeSolve dataset is the smallest one, and we think about on the small dataset, a local exploration may be more effective than the global exploration. And but in the last one, our HISCA with TSM outperforms the HISCA, right? And we think about the TSM for the genetic algorithm improved the performance of HISCA on largest dataset in our experiments. The achieved improvement of HPO performance on large dataset is more meaningful since the evaluations are more expensive. And this is the data, experiment data from systematic comparison study about the CMA-ES and TPE random search. And one thing I need to mention is random search, even simple, but you can see the random search sometimes achieved a comparable performance against TPE and random search. But anyway, TPE always achieved the best performance in all experience. And the last our experiment is about which hyperparameters to optimize. So we classify the hyperparameters into the two types: graph layer and the task-specific layers. And we find simultaneously optimize the hyperparameters from the graph layer and task-specific layers can achieve the best performance. Okay, and finally, in the future, in order to improve our HISCA, the first idea is we want to make use of the weight inheritance. So idea is already implied into the neural architecture search. So it will save the computational resource. We don't have to train the model from scratch. We can take the model from the previous evaluations to continue to train the model. And the second idea is from our last group of experiment, because we explored the two types of hyperparameters. And in the future, we want to use a random search to randomly selecting different types of hyperparameters to optimize. Probably you just choose a portion of hyperparameters to optimize, and at the same time fix some hyperparameters. And the final one is our HISCA right now. For the fast evaluation, we have a fixed setting, and based on the hyperband and the successive hiding, we probably change it to dynamically to set the epochs used in the fast evaluations. Okay, that's everything I've discussed. Thanks for everyone's attendance. And do you have any questions?
Hey, yeah, that was a nice talk. I have a couple of questions. One's just a small thing. So you're using t-tests to compare the means of distributions. Did you check that they were normal distributions before you did that?
You mean for which one?
So when you're using t-tests, so t-tests only work with normally distributed data.
Yeah.
I would normally use Mann-Whitney to compare distributions because of that.
So I use the t-test for all experiments.
Mm-hmm. Yeah, but I'm just saying that t-tests only work when the distributions you're comparing are normally distributed.
Oh, yeah, I know what you mean. But we just thought, because we run every experiment individually 30 times individually.
Mm-hmm. Okay, but in machine learning, the results are normally not normally distributed, so you have to be careful using t-tests.
Okay.
That's why I would usually use a Mann-Whitney test, which is a non-parametric test.
Okay, and do you have any suggestion for like any alternative for the t-test to qualify the?
Yeah, there's a test you can do to check whether the data is normal. So you can either do that test and then do a t-test, or you can just use a non-parametric version like a Mann-Whitney U test.
Okay, thank you.
And